Unit 6, Section 4. In this video we're going to talk about two different theorems, and they both have to do with right triangles and their altitudes. So, a similar right triangle theorem, it says if the altitude, which remember, the altitude is this line right here, and the key about the altitude is that if it's in a right triangle, it comes out of that right angle and it intersects with this other side at a right angle. So, an altitude has to be at a right angle from one of the sides and intersect with the other side. So, okay, if an altitude is drawn to the hypotenuse of a right triangle, then the two triangles formed are similar to the original triangle and to each other. So that's just saying, essentially, that there, in this picture, there are three similar triangles. So for this one, if we're going to write a similarity statement, we could say, okay, let's say I'll start with this little triangle here on the left. And the key thing about this is you have to be consistent in how you write it. So I'm going to always start with the right angle, do the short side, and then the long side. So I'm going to say triangle B, go over to A, C, is similar. I'm going to do this other triangle right here, right there, is similar to triangle. And I'm going to start with the right angle at B, do the short side, C, D, and then I'm going to do the big triangle right here. Triangle, I'm going to start with C, do the short side, A, D. And so I can pick out any of those little parts and I know that they will be similar because it was cut in half with that altitude, or it was just cut, not necessarily in half. So this example says, draw each similar triangle separately and write a similarity statement for all three triangles. So once again, if I were to kind of color code this, I'll start with this little triangle. And I'm going to do kind of the same format, so I'm always going to start with that right angle. You don't necessarily have to do this, but you just have to be consistent in how you write them. And I'm going to do the short side to the long side. And that kind of looks like, let's see, if I draw them all kind of the same, I have the right triangle, it's I, H, F. The next one, I'll do this other one in here. And so that triangle is similar to triangle, start with the right angle, I, do the short side, F, G. And so that triangle, my right angle is at I, short side goes to F, and then I have G over here. And then that one's similar to the whole big one, which is right here. That's triangle, start with the right angle, F, do the shorter side to H, and then G. Once again, if I were going to draw that, I would have, it pretty much looks the same as the original picture, F, H, G. So that's the similarity statement, and the triangle is kind of redrawn. So you can see those three similar triangles are made out of just that one picture. The next one we have is geometric mean. And geometric mean is when you do a over x equals x over b. So it's like a familiar proportion. And then if you're going to cross multiply, you can see that it would be ab equals x squared. If you did the square root of both sides, you're just going to get square root of ab equals x. And that is going to play into some side length values for these triangles, like these triangles above, where we have three triangles within one picture. So just to practice doing a geometric mean, a and b are always our numbers. And so we do 2 over x equals x over 32. So that means that 2 times 32 equals x squared. 64 equals x squared. That means x equals 8. So it's our geometric mean between 2 and 32. So if we were going to do kind of an application, the geometric mean theorem says if the altitude is drawn to the hypotenuse of a right triangle, like we're used to, then the measure of the altitude is the geometric mean between the measures of the parts of the hypotenuse. So we can think about it as setting it up like that geometric mean, or we can also just think about them as similar triangles. So the geometric mean, it's just kind of like a shortcut. So if I were going to find x, y, and z, I'm going to start with x, and I could use the geometric mean theorem to say that I have these two pieces, this one 6.5 and 26, and if I use those as a and b, I can say x over 6.5 equals 26 over x, and then I know that x squared equals 6.5 times 26, which is 169, x equals 13. I could have also thought about it as the two similar triangles and said that this leg over this leg should be similar, so the longer one over the shorter leg should be similar to the longer leg here over the shorter leg here, and I could set that up just the exact same way. So it's whichever way you want to think about it. And step 2 is to use Pythagorean theorem to find x and y. So to find y, since now I know x is 13, I'm going to write that in there. Use Pythagorean theorem to say that a squared plus b squared equals c squared. So I'm looking at that triangle there where y is c, or the hypotenuse. So I'm going to say 13 squared plus 26 squared equals y squared. If I solve that all out, I get y equals 29.1. And then to find z, since I've already found x, I'm going to use the Pythagorean theorem again to say that 6.5 squared plus 13 squared equals z squared. Because once again, this is my hypotenuse this time, and so I'm looking at these two legs. And if I solve that all out, I get that z equals 14.5. So that's kind of an application of that geometric mean in just a slightly different way. Now tune in for the last video where we're going to do the last example, which has some coordinate geometry in it.